Hey there, and welcome back to the next lesson of higher mathematics statistics. So we looked last time at how we collect data, how from a sample, how we can questionnaire, how we can avoid bias to make sure our data is accurate. We looked at how to analyze that data a bit. Now we're looking at how to represent that data as a graph or a chart or some sort, and it gives us a great like a graph with equations that we've seen before. It allows us to just kind of sit back and look at the big picture, the overall shape, the overall relationship going on. And similarly in statistics, it allows us to do that. So we're looking at a bunch of different ways we can represent data, from some of the very basic ways to the more advanced ways. So we're looking at pictographs first, where we use pictures to represent quantity of data, and it's a very simple and easy way to represent data. Then we're going to look at bar charts, where we represent data by the relative height of different bars and some of the different variations we can do on that. We're going to look at stem and leaf diagrams, which is like a diagram that actually shows all the individual data points we have. Um, so that's really handy to have. Uh, but we can also see the overall distribution as well of that data. We can look at scatter graphs, where we can almost get an equation, say, for the relationship between, say, two data sets that we might be comparing. Uh, and we look at things like correlation and the strength of those correlations. We can look at pie charts, which is a great way of comparing the relative size of various data values. Like when we've collected people into various groups and want to compare the relative size, and we've got a nice visual way of seeing that. And then finally, we can look at box plots, which is a way of seeing the key values. Like last time, we looked at averages, quartiles, and minimum maximum values. We can see that very clearly in a box plot, and compare data sets quite easily. So those are all the different types that we're going to look at. So here we go, pictographs. Pictograph uses little pictures to represent data. So here's one example. Say if we're comparing three different cities and we're comparing days of rain, and maybe we need a key like this. This is important. Um, we have each picture represents so many days of rain in say a given month, and we'll then have pictures like this. And the advantages of the pictograph is it's very simple, and it's got a very aesthetic appeal because you can, it's using pictures and things like that, and it's very easy to interpret. The disadvantage of the pictograph is that it can be less precise for large data sets, and for data sets where you've got more precise values, like fractional values, say, like here, we're just each symbol represents, say, 2 days of rain, but say if it represented, I don't know, 12 days of rain, then what, we're going to have each 1/12 of the picture. Because you see here, we've got like half pictures that represent just one as opposed to two. So there's some shortcomings of it. So once we've got this, if we know what the key is, then we can see how much data was on each of the options. Like here, for each city, we can see it was 12 days of rain, 7 days of rain, and 5 days of rain, respectively, for each of those cities. If we look at days of sun instead, you might get a question like this, and you might be told there was 6 days of sun in London. Okay, but we haven't been given a key. And what we'd have to do is we have to use that information to work out what the key is. So we've got 1.5 suns is 6. So you think, okay, what number times 1.5 would get you to 6? Or you could basically do 6 divided by 1.5 or 1.5. Typically for stats, you'll have a calculator anyway, so you'd be able to do that. And you could work out that each symbol basically represents 4 days of sun, which we could kind of tell because you see in New York and Paris, we had a quarter and a three-quarter sun. So we'd know it would have to kind of represent, uh, some multiple of 4 typically. So now we could actually work out what the others are going to be. So New York's going to be 9 and Paris is going to be 15 because New York is basically 2.25 suns. So that's 4 plus 4 plus 1. Paris represents 3.75 suns. So that's going to be 4 plus 4 plus 4. It's 12 plus another 3/4 of 4, which is 3. So comes to 15. So that's a pictograph. Very straightforward. We're going to do bar charts. So, okay, still relatively simple. Data is represented as bars like this. So we've got a graph, an axis. And say if we're considering like an ice cream vendor and they're tracking how many of different flavors of ice cream they sell, and they want to sort of see what is more popular, what's not doing so well, whatever. And we plot our data like this. because you can see you can read off then data. You can see vanilla is like something like 45 was sold, strawberry was 30, chocolate is around about 82, and so on. Kind of in the same way we read a graph, a usual graph. We can read across to the respective y values, um, and we get all these values. So the advantage of a bar chart is that it's still quite simple and we can compare values quite easily. So when we've got this picture way of seeing it, we can quite clearly see chocolate is the most popular. You can see there's not much in it between, say, vanilla and banana, or perhaps even strawberry. Um, so, and the other flavors are clearly not so popular because there's not very many of them, even though it might correspond to multiple different flavors. So there's information we can extract from this bar chart. The disadvantage of the bar chart is it's not great for large data sets. If there's many different categories, nor is it really good for continuous data. Here we've just got very discrete, uh, qualitative data here, really. Vanilla, strawberry, chocolate. That's qualitative data values. So yeah, various limitations of bar charts, but it is nice and simple. One thing, there's other types of bar chart. One you might need to be familiar with, which is like a grouped bar chart. So when you might have multiple bars that are grouped based on some category, like here, like the categories being different people, and maybe we're looking at their grades in three different subjects, English, math, and science, and we might put their bars like this. And so for Stephen has three bars, one representing his English, maths, and then science. And same thing for the others. They each have three bars each. And so rather than just maybe having an overall average score for each of them, we can then, it gives us more detail because we can see the scores of each individual subject for each individual person and compare. So we could compare science grades, compare maths grades. Again, you could see the limitations of this. If there was too many bars, this would start to get very messy and hard to read. So there's only so much you can do with this. Let's look at stem and leaf diagrams. So stem and leaf diagram. This is a great way of actually viewing all the data, that the actual raw data and its distribution. So like a pictograph, we need a key. So we have these numbers here and then a line going down. And these numbers could represent like the heights of, say, plants growing in some crop. So we've got this key 12/1 represents 121 millimeters. So you can see those first two data points, 1, 2, and then the 8 would represent 128. The 9 next to the 12 would be 129. All the way at the other end, the 0 next to the 18 would be 180 millimeters. So you've got to make sure you've got the key and you understand the key and how to read off data. The advantages of the stem leaf diagram is it retains the original values of the data set. It's not like the other ones where data is just kind of collected into pictures or bars. We can actually see each individual data point. Compact, easy to read. We can always, everything's in order as well. So we can read off things like the quartiles, median, lower quartile, upper quartile. So first of all, the median, by counting from the top and the bottom simultaneously, you'll find the midpoint is between these two values. So that's between 148 and 150. So we take the middle value of 149. The lower quartile is going to be this one. If we, now count between the 128 and the 147. So no, the 128 and the 148. Sorry, has to be strictly less than the median. So the 148 is less than the median. So we start counting from there, and you get to the midpoint. You find is 143. Likewise, counting from the 150 up to the 180, we can get the upper quartile to be 165. So that's a great thing about stem and leaf. The disadvantage of the stem and leaf diagram is that it's not suitable for large data sets. So imagine if this was really large and we had just loads of numbers, it would just be a bit overwhelming and it wouldn't be so useful because when you've got data sets that big, you don't really need to see each individual data set, each individual data point, sorry. Each individual data point becomes less important in a bigger data set. So let's see. One thing we can do like a back-to-back stem and leaf diagram, say something like this. So say if we've got another farm, maybe that's measuring their crops, like a similar crop, or the same crop and seeing their heights. And we can put them back to back like this, and it makes it easier to compare like for like. Again, we can read off the median. We could calculate the lower quartile is going to be between these two values, and we can get the upper quartile to be between those two values. So that's 170. And then compare the two, and we can see just the overall distribution. Like you see how the data is kind of lower down, which corresponds to higher crops, like higher, taller crops. So we can see that these crops are taller, which perhaps means better. The median is higher, and the upper quartile is higher. The lower quartile is slightly higher as well. So yeah, it kind of indicates that this other place is doing a bit better. So if perhaps each one is doing a different practice, you could then work out which one is actually doing the best practice, the one that's getting the best results, essentially. Um, so let's look at scatter graphs. So what is a scatter graph? So this plots two quantitative data sets against one another to observe a relationship. So it's like we're treating each data point like a coordinate almost. So we have one data point across the x-axis, one across the y-axis, essentially. So advantages of a scatter graph is that we can read individual data points, kind of like the stem and leaf. We haven't got the explicit values, but we can read it off the graph, and we can spot correlations. So let's have a look at what correlation is. So first of all, I've got a graph like this, and we're measuring like the weight and height of different people. And you see there's like a little squiggle on each of the axes. What that means is it's like a broken axis, because you see there we're not starting from zero on each of them. One of them starts from 50, the other one starts from 150, and that's what that little squiggle tends to mean, is that part of the graph is missing. Which in this case, so it's missing because there's no data there. I mean, you think about it, you wouldn't really have someone weighing less than, say, 50 kilos or being shorter than 150. That's unlikely, although it can happen, of course. Um, so we would plot um, our different people that we've got, and what we could do is we could then draw a line of correlation, which would be something like this. It's a line that is roughly just going across the data. So what we would do is we would so we've collected data from people. We've got their weight and we've got their height, and then we plot each person on this graph, on this axis, treating the weight like the x coordinate and the height like the y coordinate. So each of these points represents a person, and they've got their height and their weight we can read off on this graph, and we draw then this line that roughly goes through the progression that the data is going. And you can see like a disadvantage of the scatter graph is that, okay, like other graphs that we've seen so far, is it doesn't really work so well for large data sets. So imagine if we had a lot of data points on here, it would start to look quite messy. So typically we don't use it for really large data sets. Now, yeah, let's describe that correlation. So you see that line of correlation we've got. This is something we would describe as kind of a weak positive correlation. So we can describe the correlation as positive or negative, similarly how we have positive and negative gradients. So if it's going up, it's positive. If it's going down, it's negative. Um, and then when we say it's weak or strong, that's not really referring to the steepness. So if it's really steep, that doesn't mean it's strong. Um, it means how well are the data points um, like agreeing with that line. So are they all very close to that line, or are they a bit more spread out? And so this one is kind of a weak positive correlation because the data is kind of going that general direction, but it's a little bit spread out. Which, yeah, that kind of makes sense because you think about, you have people who have different body shapes, different builds, and so um, sometimes you could have several people of like the same height who could be of quite different weights, and so it makes sense. Height and weight are not going to be so perfectly correlated, but generally speaking, yeah, as someone gets taller, they would weigh more. So that's an example of a scatter graph. We can look at another one here, where you see only the y-axis broken this time. And we're looking at the costs of different properties based on their distance away from the city centre. So we've got the cost in thousands. So 750,000, 600,000, so on and so forth, going down. And then their distance in kilometers. So make sure you're wary of what the units are, the axes. And you see here how not only are they going down, we can draw like a rough line through it again. So this would be like our correlation. So you can see it's a negative correlation. So we see as we get further and further away from the city center, the cost of the property goes down, which is what we'd expect, really, isn't it? But you see the correlation is quite strong. Like the data points are a lot closer to the line this time, which indicates that the distance that a property is away from the city centre is quite a deciding factor in terms of how much a property will cost. Like it's quite an important factor. If the correlation is weak, then it's like it's somewhat important. But if it's very close, it's clearly an important factor. And notice we have this one point over here that doesn't really fit. So this would be an example of an outlier. So we can spot outliers relatively easily with a scatter graph, which is handy. The reason, perhaps if we try and think what could be a reason for that point, maybe, so we, looking at our line of best fit that we've done through the data, we would expect like 20 kilometers away from the city center, if we read up to the line, we would expect it to be around about, £470,000, but it's only 250. And like, what would be a possible reason for that is maybe, it's been off the property for a while. Maybe it's been damaged in some way, and so that it's being sold cheap. Um, so in order to get it sold or something like that. There could be some reason why it's suddenly going for a lot less than it should be. But yeah, so we can identify an outlier there. One last example. So we look at cars sold by, say, like a car salesman, and the rainfall in millimeters over a given month. And we might be plotting for many different months. And we see, even though you might think the amount of rainfall could potentially affect people's decisions and whether or not to buy a car, but here we can see this is an example of no correlation. I mean, if there is a correlation, it's very, very weak. We can't really see any pattern here. So this is an example of no correlation. So let's look at pie charts. So pie chart is quite nice, like a pictograph. It's quite an aesthetically appealing way of representing data. So a pie chart divides a circle into slices of a circle based on relative proportions of the data values. The advantages is that it gives you a quick visual comparison of different proportional values, how much each category makes of the whole. The disadvantages is that we can't see the individual data values very easily. I mean, we could calculate them, um, but it might not be so accurate. It's certainly not good for if we have too many categories or if any of the categories are too small. So yeah, if categories are too small, then they're going to make up very thin slices, and that's not so useful. Or if maybe if we have many, many categories, then by necessity, you're going to have some of them being very small. And so we yeah, they wouldn't work so well in those cases. So let's take an example. So say if we're at some kind of convention, like some video game convention, and we're tracking what game people preferred out of a selection of, like, say, these games, and we collect some data. What people selected as their favorite or out of these, and we now want to plot a pie chart to show the relative proportions of how popular each game was. So what we do is, first of all, we need to calculate a proportion. So remember, each slice of the circle represents how many people um, like that particular thing that is in that slice. Say Minecraft, for example, is in this slice. So we need to work out proportions. So we then know what proportion of the circle we need to give that thing. So, for example, Minecraft would then be 44 out of 150, because if we count up all those frequencies, we get to 150. So 150 people were asked in total, and 44 out of the total of 150 said Minecraft. So that's the proportion. That's our fraction that like Minecraft. And we can do the same thing for each of the others, and we get a relative proportion. And then we can then use this to work out then how many degrees of the pie chart do we need to give to that thing. So remember, we've done this before in geometry when we was looking at sectors, and we can see how much by looking at the angle in the middle, we can then determine what proportion of the whole circle that sector was. If that's not sounding familiar, yeah, go back and look at two-dimensional shapes in geometry. Um, but we're now doing things in reverse. So we've got a proportion, and then we want to use that to then find the angle. So a full circle is 360 degrees. So if we take each of these proportions and multiply them by 360 degrees, we can then find out how many degrees each slice of the pie chart needs. And so, okay, we can now take that and use that to draw our pie chart. So we start off with a single vertical line. This is going to be our radius of the circle. And then using our protractor, we can then measure an angle. So we want to measure an angle of roughly 105.6 degrees. So we can't be exact, but we get, close enough. And then we do the same thing from that new line. We now go around another 124.8 degrees. And that will be for our fortnight. And then from that line, we go down another 24. And then another 21.6 for League of Legends. And then finally, that last section should be all for Pokemon, but we can then measure it, and it should come out to roughly 84 if we've done things accurately. If it hasn't, if it's way off, then something's gone wrong. So there we go, and you see it gets quite a nice, appealing visual way of looking at that data. And clearly, then looking at that, we can see, okay, Minecraft and Fortnite are clearly the most popular. Pokemon's not too far behind, and those other two games are less popular, at least at this convention that we collected data from. Maybe the results would be very different somewhere else, so we might then want to compare and contrast with other conventions. Now, sometimes, say, an exam question might give you something like this. They might give you a pie chart like this, and they tell you the total amount of data was 150 people, and they might say use that to work out how many people picked Pokemon, for example. We can now kind of do the reverse if we wanted to. If we get out our protractor, we measure the angle that sector for Pokemon has, what their angle is. We find out it's 84 degrees. Now we know proportionally that's going to be 84 out of the total of 360 degrees. So that proportion we can times by then the total of 150, and that will take us back to the original data point of 35. So sometimes you might get in one direction where we've got the data and we need to plot the pie chart. Sometimes you might get the pie chart and they ask you to then read off the data. But you would need some piece of information. You'd have to know how many people are in one category, or maybe the overall number of people, in order to then work it out. Because all these slices, it's relative amounts, it's proportional amounts. So you need some kind of actual number, like the 150, that will ground it and give you something to actually calculate. Right, so last one, box plots. So a box plot illustrates the range and quartiles of the data set and reveals its distribution. It's really great for comparing various data sets, and we're summarizing the overall data set just by its key values. Outliers are easy to spot, and allows for easy comparisons. Like I said. So disadvantages of box plot is that it doesn't show individual data points, and it's limited to just details about the distribution as opposed to seeing the whole overall distribution, like we can perhaps see with other types of graphs, like scatter graphs, where we can see correlations, or stem and leaf, we could kind of see the distribution of the data. So yeah, pros and cons. So say if we're collecting the times for a 400-meter run of semi-pro pie chart, what this represents, what these key points represent. So we have this line here. Is each of the vertical lines represents something. This is the minimum value. This is the maximum value. We have the Q1 lower quartile is this left end of the box. The right end of the box is the upper quartile, and then the median is this red line in the middle. Typically, we use a different color for that median, but you don't have to. It's just basically the line in the middle of the box is going to be the median. So that's how we would read off from a box plot, from this one single axis that we have, which is going to represent, the data set like this. So assume, we've been given some data set and we've calculated all these, we've identified the upper value, lower value, and each of our quartiles using the techniques we learned in the last lesson. And we've got this table of data. we can then use that to plot this. So I put in the lower value, upper value. So you just read along the axis and find out where those values are. I can put in the lower quartile and upper quartile. Then I draw in the median. And then now we just put in the horizontal lines, which don't mean anything. They just create the blocks and what are sometimes referred to as the whiskers, because they're like whiskers of a cat popping out. That's another name for this. Is sometimes, box and whisker plot, but I just call it box plot. And so once we've got something like this, we can kind of compare the two quite nicely. Like we can see, so say if you was asked to compare and contrast, we can see that this second data set that we've done, it seems to be more consistent because you can see the minimum value and the maximum value are tighter in. There seems to be more spread with the first one we plotted. But this second one, you can see that that within its range it's got a bit of a broader box. So yeah, that central region does seem to be a bit more spread out. You can see that the median in the first box plot is more near the middle, whereas in the second box plot it's more towards the left. So we can see that that second box plot, that second group of people that we tested, their the data is kind of skewed more towards the lower end, so it's kind of leaning more that way than it is towards the upper end. So there's various things we could say about this, and maybe you would then use this data to then choose which team or something. If this were two different teams, which team maybe you want to move forward with or something to like a pro level, something like that. That'd be an example. One last thing that I haven't included here, which is say if you had outliers. So like what we did last time, you remember we had that little formula using the interquartile range. We could then estimate what an outlier is. If we do identify an outlier, sometimes you just want to remove it from the data set. It all depends. Say if we had an outlier like in that second group, but maybe it was like at 70 seconds, like and if we wanted to include it on the graph, we put it outside of this as just a little X at that point on the graph. And sometimes we wouldn't include it at all. It depends on what the reasons is. So say if we had someone who did, in that second group, they got a time of 70 seconds, where you can see that sort of way away from any of the other, from the actual box plot. And maybe our reasoning for that was, because they'd sprained their ankle or, they wasn't very well that day. And that caused them to then have a much slower time. And so we chose to just remove that from the data set because it's not really representative of their true ability, something like that. So there's various times like that where we might eliminate data points because they're not actually helpful. So there we go. Okay. But if we were going to include it, it'd be like just a little X. So that's it. So let me leave you with did you know that there's a growing field of statistics in modern years where data scientists try to deal with extremely large and growing data sets. So this is like a job title, data scientist, someone who studies data and tries to find patterns. And but there's a new field called big data where it's dealing with data sets that are so incredibly large. The data scientists have to kind of be inventing new methods to analyze them. So you have like big companies like Netflix, Google, YouTube that you're probably quite familiar with. They collect not only huge amounts of data, but the flow of new data coming in all the time is just astronomically huge. And it needs to be analyzed quickly so that these companies can stay up with common trends, like modern trends, and obviously succeed. So these data scientists are trying to do that to keep up with data and keep up with the technology, which is constantly improving and increasing the flow of data even faster. So yeah, this is a really growing and an important field of like data science. So if you're interested in this kind of stuff, if you like data and you like studying it and looking for patterns and things like that, this would be a great career choice to go down into big data. That's what the field is literally called, big data. But here you go. This is our takeaways for today's lesson. So that's it. We've kind of done a lot of what we need to know regarding statistics. Next time, we're going to be looking at some last more challenging areas of statistics, which is do frequency tables, group frequency tables, and we're going to look at some more tricky plots like histograms. Uh, so I will see you in the next lesson for last lesson on statistics.